Hello teacher, this is my paper title, Optimizing the Hybrid ML to DL Model for Credit Risk Assessment Using High-Dimensional Data Filter Selection. My name is Zhou Baitong. My student number is 232029666. My advisor is Kakawa. My paper is divided into 7 parts. Chapter 1 is Introduction. Banks phase 3 crisis, high-dimensional noise, 16% filter redundancy, 0.8% monthly model decay, and regulatory black boxes violating Basel IV architecture 413. Consequences include $14 MS capital misallocation and 14% ROI erosion during model failure. We introduced DFS to DRNet, a triple innovation framework featuring dynamic dimensionality reduction, 14% is redundancy elimination, temporal draft correction, and editable filter contributions. These 5% variance. Validation targets: 93 points per 2% filter information retention. AUC drop less or equal 0.8%. BCBS 2023 certification pass. Industrial impact prevents $MS capital misallocation and enables phonetic scalability. 7-phase methodology: literature review, theoretical foundations, framework design, module development, experimental validation, implementation, white paper. Deliverables, open source library, 500 KA sample dataset, and regulatory adult prototype. Chapter 2 is literature review. Credit modeling evolved from logistic regression to hybrid systems. Critical gap: current filter selection methods can't handle greater 10K dimensions with 16% redundancy. Our breakthrough addresses this multi-dimensional complexity. Literature links solutions for dynamic filter draft, 0.8% monthly decay, and regulatory grade interpretability. We bridge this gap with temporal adaptation and Basel compliance explainability. Chapter 3 is theoretical basis and problem analysis. Foundations: matters PD model, EL equal PD times LGD times EAD calculation, regulatory mandates, retention of 5 core financial regions, and monotonic decision boundaries. Hybrid approach combines logistic regression with non-parametric trees. Innovative temporal attention mechanism formula shown with KO divergence monitoring for non-stationarity. Regulatory compliance enforces those regulations, constraining future contribution variance. Design treated. Performance explainability trade-off FRCR greater or equal 0.9. Residual connections for gradient flow and built-in sharp interpretability for gratitude explanation. Code advances: dynamic filter selection with regulatory constraints, hybrid architecture enabling 14% faster coverages, and compliance by design resolving the accuracy interpretability conflict. Chapter 4 is methodological framework design. 3-layer design, filter selection, 83.8% dimensionality reduction, model function attributes to CNN ensemble, and dynamic optimization. Key innovation: filter bridging and recycle reuse. Dual channel filtering, static, enhanced RF with Gini mutual information, and dynamic. Achieves 587 to 95 filter reduction while retaining regulatory critical variables. Cascaded attributes LSTM with lift to improve filter transfer. Residual connections accelerate coverages by 14%. Training protocols, grading clamping, normal equal 1, and audit trial filter preservation. Bayesian optimization with Gaussian process, segregate, and constraint-aware ER echo question. Adaptive weighting with change limits. Outcome 37% lower KI's drift volatility. Chapter 5 is experimental design and result analysis. Data size. Landing club and Kaggle created default. Progressing. K importation, UI joining normalization, smooth ENN resampling, temporal split, pre or post 22 data. 587 to 95 filters. It's 3.8% reduction with 93.2% information retention. Critical filters solved debate to income and all based 3 core variables. The hybrid model AUC reached 0.872, significantly ahead, 7.4% higher than SG Boost and 5.4% higher than SG Boost 8LR. Segmentation advantage, the recall rate of high-quality customers increased by 12.3%, and the misjudgment rate to high-risk groups decreased by 9.8%. The residual structure accelerated the convergence by 14%. Imbalanced data 9 to 1. Focal loss achieves F1 equal 0.89 vs smooth 0.81. Concept draft 2020 to 23. AUC drop limited to 3.2% vs 8.7% baseline. Passed all 12 ECB prime tests with at least 1.2% annual decay. Chapter 6 is application and discussion. Standard chartered hybrid development with 5MS model switching, real-time FX integration, results 2.4% ROI increase, 0 fines. HSBC faced migration with automated compliance reporting. 3-tier compliance, reject inference engine, group shape analysis, and model interpretation review board with quarterly add-ons and 200% documentation coverage. Esteem challenges: 1. Privacy united conflict. 2. High-risk group bars. 3. Real-time bottleneck. This will be the key breakthrough direction in the future. Chapter 7 is conclusions and future work. 3 major breakthroughs. 1. TFAN future network achieved a 3.8% dimensionality reduction. 2. SG Boost LSTM Cascade improved AUC by 7.4%. 3. Dynamic optimizer controlled annual decay leads 1.2%. The results were ratified by 2.7 million lawyers and provided a new program for compliance AI. Next steps: 1. Develop zero knowledge sharp proofs to address privacy issues. 2. Establish a unified compliance framework across the EU, US, Singapore. 3. Edge AI optimization target latency least 5% MS. This requires collaborative advancement by industrial, academia, and research. I would like to express my sincere gratitude to Tutor Kakawa for his careful guidance and the reviewers for their valuable time.